Good morning. I'll pass on to the second numerical example in rigid frame analysis by flexibility method. Let's consider a rigid frame as shown in figure. So first step in flexibility method is always identify the static indeterminacy. Here the static indeterminacy, number of unknowns minus the known equations of equilibrium. So the unknowns are at fixed support there is 1, 2, 3 unknowns: vertical reaction, horizontal reaction and moment. In the roller there is only one reaction, vertical, normal to the surface of the roller, a vertical reaction. So altogether 3 plus 1, 4 unknowns, 3 equations of equilibrium. So the indeterminacy is 1, or the redundancy of the structure is 1. So you have to remove any one redundant. I am going to remove this roller here. I am going to release RC, or I am going to release that redundant, or I can say remove roller at D and get the primary structure. So the primary structure is going to be like this. And in the primary structure, this is the load acting A, B, C. So this is the primary structure with external load. And I have to mark the redundant. So this is the primary structure. Redundant is the reaction at C. I am going to mark the reaction at C. So I am going to mark downwards. Doesn't matter if you mark it upward. I am going to assume it as a downward reaction. Let us see if we get the result as negative. It is opposite. So I am going to mark redundant. So this is the primary structure with redundant. A, B, C. So the point C. I am going to mark the element coordinates also. Because to write the transformation matrix, we have to define the coordinates. Any one element can be taken as 1 and 2. So it is our discretion which element has to be treated as the first element and which has to be taken as the second element. What should be the direction of the internal moments? Everything is left to the analyst. I am going to take this as the first element, A. So this is P1 of A, clockwise moment. This is P2 of A, clockwise moment. Second element B, this P1 of B and P2 of B. This is called the element coordinates. All these come under step 2. So first step is you identify the redundant. In the second step, you release the redundant, obtain the primary structure. On the primary structure, you mark the external load as well as the redundants and define the element coordinate system. Now, before forming the transformation matrix in the next step, what we have to do is the element AB is having load on the span. This has to be transformed to the equivalent joint loads acting in the nodes A and B. So the third step is equivalent joint load, or from that we have to get the analysis structure. Equivalent joint load, obtain the equivalent joint load, and from that you obtain the analysis structure. So consider this element AB. Let us assume it as both ends fixed and find out corresponding to this 10 kilonewton per meter UDL A, B, and the span of the beam is 4 meter. So what are the fixed end moments? If you stand in this direction and view it in this way, so this left end, it is W L square by 12. Anti-clockwise, the value happens to be 10 into 4 square by 12, 13.33 kilonewton meter. In this sense, the moment is clockwise, 13.33. So these are the two fixed end moments. Now, For this, there will be reactions. 10 into 4, 40 is the load. So there will be a reaction of 20 kilonewton, 10 into 4 by 2. And here also there will be a reaction, 20 kilonewton. So these are the fixed end moment and reactions of element AB. So this load is equivalent to these two moments and these two reactions acting here. Now what is equivalent joint load? Just reverse it. This is the fixed end moment. So the equivalent joint load will be this 13.33 clockwise moment. You reverse it. It will be anti-clockwise 13.33 kilonewton meter. The load acting towards left 20 reaction has to be marked like this. This is 20 kilonewton. In the support anti-clockwise, so we mark it as clockwise 13.33 kilonewton meter. I will mark it here. This 20 has to be marked opposite to that 20. So this is the equivalent joint load. This element goes like this. Joint B, joint A, this end C. So the fixed end moment and reactions are just reversed to obtain the equivalent joint load. Now the analysis structure is the one in which we can delete those reaction components or the fixed support, or those reaction components or those load components which will not produce any bending moment anywhere in the beam. As such, the fixed end moment here, this is a fixed support, that is a support reaction. This horizontal this reaction is also a fixed support reaction. These will not produce any bending moment anywhere in this column AB or in this beam BC. So we can delete these two components. So we can write here, we can delete moment and reaction at A. So even if we ignore these two things, the problem analysis will remain the same. Whereas this load, this will produce bending in this column, this 20 kilonewton. This moment, that will also produce a bending moment in this column. Right. And for the beam BC, there will not be any bending moment or no bending moment due to any of these two loads. This will be acting as the axial force in the element BC only. So this 20 kilonewton and this 13.33 kilonewton acting at joint B has to be considered in the analysis, whereas we can neglect or we can delete these two values for the analysis, and the structure obtained after deleting the moment and reactions at the support A, at the fixed support. So it will be an anti-clockwise moment here, 13.33 kilonewton meter, and a horizontal load at this joint, 20 kilonewton. I'll take this as P1, I'll take this as P2. So this is going to be the analysis structure. So the analysis structure is obtained after deleting the moment and reaction at fixed end. So now the entire problem of solution of this question, it is transformed into a structure with this one redundant plus a structure with this nodal load 20 kilonewton at a moment 13.33 at B. So if you analyze a structure which is a combination of this redundant primary structure with redundant and the primary structure with these two loads, that is equivalent to analyzing this particular structure. Now let us come to the remaining steps are very much familiar to you. The force transformation matrix. Put P1 equal to 1. Find out the bending moment values at the two ends of the two elements. P2 is equal to 1. Get the bending moment at the two ends of the two elements. R1 equal to 1. Then the remaining process is simply multiplication of matrices. So pass on to the third step. So now let us discuss the step 3, force transformation matrix formulation. Consider the first element. Consider the first figure. This is P1 equal to 1. P1 equal to 1. This column AB. It is an anti-clockwise moment. That is, it tends to push the beam inward, or this is going to produce a sagging moment. A moment which tends to push it inward. This is sagging moment. So from the anti-clockwise, from the base, here it is anti-clockwise. 1, 1. So a sagging moment. You can see a sagging moment is which tends to bend the beam inward, like this. Now, when P2 is equal to 1, this tends to bend the beam outward, or it produces a hogging moment. And this is 1 into 4, 4, a hogging moment from the base to the ordinate. When R1 equal to 1, this tends to bend the beam up. So 1 into 2, it is 2. And if this is hogging anti-clockwise, so here it should be hogging itself everywhere. It is 2. This is the original frame. Bending moment diagram is drawn in the blue color. This is anti-clockwise, this is clockwise, this is anti-clockwise. So it's very simple now. The problem has become apply the loads one by one, the redundant, and draw the bending moment diagrams. Now we can write the force transformation matrix. There are two elements, P1 of A, P2 of A, P1 of B, P2 of B. Just right. By applying capital P1 external load unit value here, the first end of the first element, this is the first end, it is plus 1. And the second end, it is minus 1. And for this element B, both these are 0, 0. By applying P2 is equal to 1, first element minus 4, 0 and 0, 0. We are going to separate it. When R1 is equal to 1, first element minus 2 plus 2 minus 2, 0. This into P1, P2, R1. So this forms A suffix P and this is A suffix R. So we have got the transformation matrix. Next step is, so this is step 3. Now coming to step 4, alpha bar, unassembled flexibility matrix. For the first element alpha A, it is L by 6 EI, 4 by 6 EI, 2 minus 1 minus 1, 2. For that the EI value is I only. For the second element alpha B, the length is 2 by 6E, the moment of inertia is 2I into 2 minus 1 minus 1, 2. So I can rewrite it as the alpha bar matrix. This is 4 by 6 EI, this 2 against cancels, become 1 by 6 EI. If I make it as 1 by 6 EI, if take it as common factor, the first one, it will become 8 minus 4 minus 4, 8. The second one, 2 minus 1 minus 1, 2. The remaining elements are 0. So this is the alpha bar matrix. Now step 5, we can do FRR, AR transpose alpha bar into AR. So this is AR. AR transpose means minus 2, 2, minus 2, 2 into this 8 minus 4 minus 4, 8, 2 minus 1 minus 1, 2. Again AR, this into minus 2, 2, minus 2, 0. After this multiplication, you will get, it is 1 by 6 EI into 104. Because there is only one redundant, it will be a matrix with single element, one element only. Second step, FRP. FRP equals AR transpose alpha bar into AP. AR transpose alpha bar you can get from this and multiply with AP. A suffix P. It's a 4 by 2 matrix. So you'll get the answer as 1 by 6 EI minus 48, 96. Now this FRP into P. FRP into P will be 1 by 6 EI minus 48, 96 into P. There are two elements P1 and P2. P1 is 13.33, the bending moment value at the node B. And P2 is the horizontal load, that is 20. It will work out to 1 by 6 EI 1, 2, 8, 0. Next, FRR into R is equal to minus of FRP into P. So that 1 by 6 EI into 104 R1 is equal to 1 by 6 EI FRP into P is 1280 minus 1280. Solving that, you will get R1 is equal to minus 12.31. That means the reaction at that support C is opposite to the sign which you have assumed. I have assumed downward, but the reaction is 12.31 upwards. So now coming to the last step, final moments. Final moments, M is equal to fixed end moment plus element forces. So element forces you can obtain from step 3. It is written here, I have not cancelled it. This is the step 3 value. So the element forces can be obtained as transformation matrix into P1, P2, R1. Substitute the value of P1 and P2 and R1. P1 is 13.33. P2 is 20 and the R1 value is minus 12.31. Doing this multiplication, you will get the element forces as minus 42.07, minus 37.93, 24.6 and 0. So coming back to this, you have to get first element MAB, MBA, second element MBC, MCB. Fixed end moment. For the first element, there were fixed end moment minus 13.33 and 13.33. For the second element, there was no fixed end moment. That plus the values which you get from this step, minus 42.07, minus 37.93, 24.60. This will work out to minus 55.4 minus 24.6, 24.6 and 0. So these are the final moments. Now we have to draw the bending moment diagram. For drawing the bending moment diagram, draw the given structure. Draw some rollers. This is element A, B, C. For the first element, MAB is minus 55.4. So A to B minus anti-clockwise minus 55.4 kilo Newton meter. The second then it is minus 24.6 from here anti-clockwise. So 24.6. This is 24.6. Then plus 24.6 here to here clockwise. So this is 24.6. Here to 0. So we have drawn the fixed and moment values, or the internal moment values are the support moments. Now in this element there was UDL. So you have to superimpose. You have to draw the free bending moment diagram. And this value at the center is going to be W L square by 8. It works out to 20. This is 20 kilonewton meter. Now I have to mark the signs. So a sagging moment diagram is superimposed over the sagging moment. So the remaining portion is only this much. And all these portions are sagging. Everywhere it is sagging. And only this portion is in hogging. That is the bending moment diagram. With that, we come to the end of the analysis of rigid frames by flexibility method element approach. Thank you.